Hello, everyone. Today we're going to be talking about neutralization reactions, also known as acid-base reactions. So, we've talked about acids and bases and defined them, but here's a quick review. So, an acid is something that produces hydrogen ion, or H plus, in solution. And the more H plus it produces, the more acidic it is. That can be because you're adding more acid, right? If you add more acid, the solution will be more acidic. Or if you have a strong acid, they release more hydrogen ions than a weak acid does. So there's different variables that go into this, but essentially the more H plus in a solution, the more acidic that solution is. Bases are something that creates hydroxide or OH minus in solution. And that can be done several ways, right? We have our Bronsted-Lowry bases, we have our Arrhenius bases, but the end result is that it creates more hydroxide one way or the other in the solution. And the same concept applies here. The more hydroxide is present, the more basic a solution is. So when an acid and a base are mixed, right, acids have lots of H plus, hydroxides have lots of OH minus. When we mix those together, we get this very simple reaction of the hydrogen ion and the hydroxide ion combining, and they form water, or H2O. So this is the basic concept of a neutralization reaction. We have the acid portion reacting with or neutralized by the base portion here, and we end up with nice neutral water. So that's our definition, right? Our definition of a neutralization reaction is when we have an acid reacting with a base, and it always produces two things. It produces a salt, which, remember, that's a much broader term in chemistry, and water. So a salt is any ionic compound, because an acid isn't just the hydrogen floating around. That was attached to something else at some point, something we call the conjugate base. Same thing with the hydroxide that has the conjugate acid. And those two remainders come together and form our salt. It can be something simple like sodium chloride, the table salt that we're used to, or strontium fluoride, right? That's an ionic compound because we have a metal bonded to a non-metal here. So we want to be able to write out the reaction for when we have an acid and a base neutralizing each other. So to do that, we need to have, first off, an acid. Here we have hydrochloric acid, and a base. Here we have sodium hydroxide. It's a very simple example. So hydrochloric acid, if we think back to our naming, if we have the hydro out in front, that means that it's just a binary acid, meaning it's hydrogen and one other element. That one other element is going to be chlorine. We can tell from the chloric ending to our name here. So hydrochloric acid is HCl. Again, this dissociates or breaks apart into hydrogen, which has a +1 charge, and chloride, which has a -1 charge. Again, we either know these charges or we can find them on our periodic table. Since hydrogen's in group 1A, it's always going to be +1. Chlorine's in group 7A, it's always going to be -1, like all of the other halogens over there. Sodium hydroxide, very similar. We have sodium also in group 1A, right? That has the +1 charge, and hydroxide with a -1 charge as our anion. This is our base because it has hydroxide. This is our acid because it has the hydrogen here. So this reaction is just a double replacement reaction. We've talked about that before. We have two different compounds. We have hydrochloric acid and sodium hydroxide. It's a double replacement reaction because the cations, the front parts with the positive charge, those are switching partners, right? So we switch partners between our cations and our anions, and we form water, which comes from the hydrogen and the hydroxide, and a salt or ionic compound from the sodium and the chloride in this case. It's important, though, that we balance our charges in the products in order to have the correct products being formed. So here, again, we have hydrochloric acid and sodium hydroxide. I've written in the charges here just so we can recall what the charges are. That way, when we switch partners, we have sodium with a +1 charge, chlorine with a 1- charge. Those are equal, so we just need one of each. Then we have the hydrogen and the hydroxide, also +1, -1, so we only need one of each. Our final formula, though, for the final overall reaction would not include these charges, right? I just have them written here so that we know how many of each we need to have the correct product. So our final reaction would look like this. We have hydrochloric acid, which is aqueous, plus sodium hydroxide, also aqueous, that produces sodium chloride and water, which is a liquid. So that was a nice simple example, just 1-to-1, since everything had a plus or minus 1 charge. However, that's not always going to be the case. Here we have another reaction with hydrochloric acid, except this time it's neutralizing barium hydroxide. So we have a different base here. So hydrochloric acid, same thing. We have the hydrogen, the chlorine. Hydrogen is +1, chlorine is a 1-. Barium hydroxide, however, since barium is an alkaline earth metal in group 2A, it's going to have that 2+ charge. The hydroxide still has -1. So in order to have an overall neutral compound here, for every 1 barium, we need 2 negatively charged hydroxides to cancel that out. So when it breaks apart or dissociates, this is what it looks like. And that comes into play later on. So again, it's still just a double displacement reaction. We're still switching partners, but we need to be sure to balance the charges when we're forming our products. So over here, we have hydrochloric acid, we have barium and hydroxide. So when we are switching our cations, now the barium bonds with the chlorine here. Since barium has a 2+ charge and chlorine has a 1- charge, we need to have 2 chlorines in order to cancel out the 2+ charge from the barium. So it'd be Ba with 2 Cl's here. And then the other product is 1 hydrogen for every hydroxide. So our products would look like this. We have HCl plus barium hydroxide, which we got from up here, is producing barium chloride, which is BaCl2. Again, we have 2 chlorines for every 1 barium based on these charges here, plus water. So our salt in this case is barium chloride, which we got the barium from our base, the chlorine from our acid. Now, those of you who are keeping an eye out might notice that we are not balanced, right? This needs to be balanced to be the correct answer here. Since we only have 1 chlorine on the reactant side and 2 chlorines on the product side, we know we're not balanced. We also have a different number of oxygens. We have 2 oxygens here versus only 1 oxygen here. So we have an issue. To balance this, all we need to do is add a 2 in front of our hydrochloric acid here to give us 2 chlorines and 2 chlorines. And then now we have 2 hydrogen, 2 hydrogen, for a total of 4 hydrogen on our reactant side and 2 oxygen. That's enough to make 2 waters on our product side here. So for every hydrogen and hydroxide, in this case we have 2 of each, we're going to be making a water. So since we have 2 of each, we're making 2 water molecules. So next up, the calculations for these neutralization reactions. So a neutral solution, one that's not acidic or basic, is one that has the same number of moles of H+ as it does moles of OH-. If you have the same amount of acid as you do base here, you're going to have an overall neutral solution. So since the molarity equals moles over liters, right? We spent a lot of time working with this in our last unit. We can have a pretty simple formula that looks a lot like our dilution formula from before, that M1V1 equals M2V2. For acid and base neutralization, we have this. We have the number of acidic hydrogens on the acid times the molarity of the acid times the volume of the acid is equal to the number of hydroxides on our base times the molarity of the base times the volume of the base. So it looks a lot like our M1V1 equals M2V2, but we have to keep in mind how many hydrogens are on our acid and how many hydroxides are on our base here. So let's give it a shot. Let's start off with another pretty simple example. Move myself out of the way. So I want to know How many milliliters of 4 molar hydrochloric acid is needed to neutralize 200 milliliters of 2.5 molar sodium hydroxide? So again, we're just going to be using this equation right here. We just need to go through step by step and identify what numbers we can plug in for each of these variables. So we start off on the left and make our way across. For the number of hydrogens in our acid. Our acid is hydrochloric acid. We look at our formula here. How many hydrogens do we have? We just have one, right? So we would have one acidic hydrogen here, and that would be the value that we're going to plug in there eventually. So how many hydrogens are present in our acid? Our answer would be 1. Next up, the molarity of our acid. We read through, it says how many milliliters of 4 molar HCl. So we know the concentration. The concentration of our acid is going to be 4 molar. Next up, the volume of our acid. The question says how many milliliters of 4 molar HCl is needed to neutralize, and then gives us information about our base. So it doesn't tell us the volume of our acid, right? That's going to be what we're trying to find. That's our variable that we're trying to solve for using this equation. So the volume of our acids are unknown. So when we're plugging that in, we just plug in the variable, in this case VA for volume of acid. So that's it for the left-hand side. Now we can move over to the information about our base on the right-hand side. So we have number of hydroxides. So if we look over here at our base, sodium hydroxide, in this formula, we only have one set of hydroxide here, right? So the number of hydroxide ions per molecule of the base is just 1. Next up, the molarity of our base. It says is needed to neutralize 200 milliliters, that's our volume, of 2.5 molar sodium hydroxide. So the concentration or the molarity of our base, our MB, is going to be 2.5 molar. Lastly, we need the volume of our base, and it says we have 200 milliliters of our base. So that's going to be our VB, or the volume of the base that we have. So now that we've gone through and identified all 6 of these variables here, we just plug them in. So we plug in 1 into our number of acid hydrogens here, the molarity of 4 into MA. For our volume of our acid, what we're trying to find, we just keep it as our variable, VA. Then on the base side, we plug in 1 for the number of hydroxides, 2.5 molar for our molarity, and 200 milliliters for our volume. We end up with an equation that looks like this. We have 1 times 4 molar times our volume equals 1 times 2.5 times 200 milliliters here. So now to solve for our variable, since we only have one variable here, we just need to move everything to the opposite side of that variable. So how I would do this, I would multiply everything on this side first, right? I have 1 times 2.5 times 200. If you plug that into your calculator, you end up with 500 milliliters. Then, if you do 500 milliliters divided by, to get rid of these, you'd have to divide by 1 times 4 is just 4. So divide by 4, we end up with 500 divided by 4, which gives us our final volume, the volume of the acid needed to have a neutral solution, 125 milliliters of this acid. So again, it's just like our dilution equation, but we need to keep in mind the number of acid hydrogens and the number of base hydroxides that are present. Okay, so here's a second example. I want to know how many milliliters of 3 molar calcium hydroxide is needed to neutralize 50 milliliters of 1 molar phosphoric acid. So this one has slightly different numbers because we have calcium hydroxide, which has 2 hydroxides for every molecule of our base. And then our acid here is a polyprotic acid, and phosphoric acid meaning has 3 acidic hydrogens. So again, we just use this equation here. I'm going to walk through it a little slower, give you some time to do it on your own. So first thing we're going to identify is how many acidic hydrogens are present and how many hydroxides are present. Pause the video, give yourself a second to do this. All right, so if we look at our acid, right, our acid here, we have 3 hydrogens out front. Those are our acidic hydrogens. So the number of hydrogens would be 3. And the number of hydroxides in our base would be 2 hydroxides in our base, right? Because we have 2 hydroxides for every 1 formula unit right here. Next up, we need to find the molarity of the 2. So the molarity of our acid, it tells us is 1 molar right here. The molarity of our base, it tells us is 3 molar right here. So now we know Ma and Mb. Lastly, we need to find out the volume of our acid and the volume of our base. So for the volume of our acid, it says is needed to neutralize 50 milliliters of 1 molar phosphoric acid here. That would be our volume. The volume of our base would be our variable. It's asking how many milliliters of 3 molar calcium hydroxide is needed. So that's going to be our variable. That's what we're trying to solve for, is VB, or the volume of our base here. So once you have all those numbers, you can again just plug them into our equation. Our only one we shouldn't have something to plug in for is what we're trying to solve for, which is VB in this problem. We end up getting something like this, right? 3 acidic hydrogens times 1 molarity times the volume of 50 milliliters. Then we have 2 for the number of hydroxides. We have 3 molar, and we have the volume of our base here. So to solve for VB, all we have to do is divide both sides by 2 times 3 is 6. Divide both sides by 6. We end up with 150 divided by 6. That gives us a VB, or the amount of base needed, of 25 milliliters. We would need 25 milliliters of this base in order to neutralize or make it not basic or acidic anymore, this volume of 1 molar phosphoric acid.